coding agent secured the chat app in 3 seconds by adding TLS green padlock in the browser. Data encrypted in transit. So what exactly is your job now? Here is what AI did not do. Realize that TLS only encrypts the tunnel. The moment the message hits the server, it is decrypted in plain text for any database engineer or hacker to read. AI secures the pipe. You design end-to-end encryption using the signal protocol to secure the payload before it ever leaves the phone. That judgment call is the one that guarantees absolute privacy for 2 billion users. After this video, you will be able to make it and explain exactly why. That is the skill that survives. 5 things you will own after this video. Why standard HTTPS encryption is not enough to protect a chat app. The exact mechanics of the signal protocol using public and private keys. Perfect forward secrecy via the Double Ratchet algorithm. Guaranteeing that if a hacker steals your key today, they still cannot read yesterday's messages. The massive architectural trade-off AI misses when asked to design this. And the survival skill, mistrusting your own servers. If you watch this video to the end, you will be able to answer an encryption interview question better than 99% of candidates who have been building software for years. Let us start with what breaks. Imagine hiring an armored truck to transport a transparent glass box full of cash. The truck is bulletproof, that is TLS or HTTPS. Nobody on the highway can touch your message. The message leaves the user's device encrypted. Nobody intercepting the network traffic can read it. But when the truck arrives at the WhatsApp server, the TLS tunnel terminates. The message pops out in plain text. The server has to read the message to figure out where to route it or to save it to a database. If a rogue database administrator, a government subpoena, or a hacker gains access to that server, they can read every single message sent by 2 billion users. The standard HTTPS approach breaks the core promise of WhatsApp instantly. This is the problem that forces end-to-end encryption. Not because HTTPS is bad, because the constraint of absolute privacy means the server itself must be treated as hostile. That constraint is the entire reason for everything that comes next. Instead of just putting a glass box in an armored truck, imagine putting the message inside a heavy steel safe. You lock it and you do not have the key. The truck driver does not have the key. Only the person receiving the safe has the key. Even if the truck crashes, the safe remains locked. That is end-to-end encryption using asymmetric cryptography. User A locks the message on their phone. The WhatsApp server just moves the lock safe. User B unlocks it on their phone. The server sees nothing but scrambled data. This is achieved using the Signal protocol. When you install WhatsApp, your phone generates 2 cryptographic keys. The private key stays on your phone and never touches the internet. It is the only thing that can decrypt your messages. The public key is uploaded to WhatsApp server. It acts like an open padlock. If user A wants to message user B, they ask WhatsApp for user B's public key. User A uses it to lock the message. Once locked, not even user A can unlock it. Only user B's private key can decrypt the payload. Every architecture trades one thing for another. If the server cannot read the messages, the server cannot search them. You cannot type a keyword and have the server find an old chat. The search must happen locally on your phone's processor. Cloud backups become incredibly complex. But WhatsApp cannot compromise on privacy. The loss of server-side utility is the mandatory cost of mathematical security. That is the constraint-based reasoning that separates a developer from an engineer. The developer turns on TLS, the engineer implements the Signal protocol. Now, how does WhatsApp prevent a hacker from stealing your private key today and reading all your past messages? Let us look at the double ratchet. If your private key is your master password, what happens if someone steals your phone today? Can they download your encrypted history and decrypt it all? Not with the Signal protocol. WhatsApp uses the double ratchet algorithm. For the very first message, it generates a temporary session key derived from the master keys. Message 1 is encrypted with key 1. But here is the genius part. The act of sending message 1 mathematically generates session key 2. The ratchet turns forward. It cannot be turned backward. Message 2 is encrypted with key 2. Every single message uses a brand new unique encryption key. If a hacker compromises your phone today and steals session key 100, they can only read future messages. Because cryptographic hash functions are one way, they cannot mathematically reverse key 100 to figure out what key 2 was. Your past messages remain permanently encrypted. This is called perfect forward secrecy. If this kind of judgment call, designing systems that assume they will eventually be compromised, is what you want to make, confidently, subscribe now. Every Tuesday, one system design judgment call free. Now let us see exactly where TLS fails by comparison and why the trade-off is non-negotiable. With TLS, messages are decrypted in RAM at the load balancer. They are readable by server admins, cloud providers, and hackers. With E2EE, the server only routes encrypted blobs. It is mathematically impossible for the server to read them. With TLS, it is easy to implement server-side search, spam filtering, and AI chatbots. With E2EE, it is extremely difficult. All text processing and searching must happen locally, draining the device battery. Ask an AI to secure a chat app, and it generates an HTTPS certificate, logically correct for the network, a complete failure for data privacy. The engineer defaults to the constraint. The answer is not use encryption. The answer is the product constraint dictates the server is a hostile environment. We must use asymmetric cryptography and perfect forward secrecy. That answer is the one that gets you hired. Let us put it all together one final time. The full system in one clean view. Full system, every component visible. Here is the complete journey of a message secured by the Signal protocol. User A wants to send a message. First, the app requests user B's public key from the WhatsApp key server. The key server returns it. This happens once per session. User A's phone uses the public key and a unique session key to encrypt the payload. The phone sends the scrambled blob to the Erlang chat server. The chat server has no idea what the message says. It only sees the routing headers. It pushes the blob to user B's open connection. User B receives the blob. Their phone uses their private key, which has never left the device, to decrypt the payload. Instantly, both phones run the Double Ratchet algorithm to throw away that session key and generate a new one for the next message. 6 hops, absolute mathematical privacy. Before this video, the answer to how does WhatsApp encrypt messages was they use HTTPS. After this video, the answer is HTTPS leaves data exposed in RAM. WhatsApp uses asymmetric cryptography to lock payloads on the device and the double ratchet algorithm to guarantee perfect forward secrecy. That shift is the judgment call that no AI prompt can generate. That shift is your job. You now own the architecture. Last piece, how do you walk an interviewer through this in 45 minutes? That is next. 45 minutes, blank whiteboard. Most candidates start drawing immediately. That is the first mistake. Phase 1 is clarifying constraints. Ask the interviewer, are we building a standard enterprise chat like Slack, where the company owns the data, or a privacy first app like WhatsApp, where even we cannot read it? That single question separates you from 90% of the room. Phase 2, propose the naive approach. Say out loud that TLS is mandatory, but explain exactly why TLS termination at the load balancer creates a massive internal vulnerability. Prove you know why it fails. Phase 3, introduce the solution. Explain public and private key pairs. The sender encrypts with the receiver's public key. The receiver decrypts with their private key. Phase 4, security edge cases. The interviewer will ask, what happens if a phone is stolen? Your answer is perfect forward secrecy using the double ratchet algorithm, rotating session keys per message. Finally, phase 5, the trade-offs. Acknowledge that E2EE makes cloud backups, multi-device sync, and server-side search incredibly difficult. Those are the engineering taxes you pay for absolute privacy. Before this video, use a secure connection. After this video, the constraint of absolute privacy means the server itself is a hostile environment. Asymmetric cryptography and perfect forward secrecy are the only structures that fit. The engineer who can say that in an interview, in a system design discussion, in a code review, that engineer is the one who built the system. Everyone else installed an SSL certificate after the decision was made. That distinction is your survival skill. Next Tuesday, real time messaging architecture. When user A and user B are connected to completely different servers, how do the servers talk to each other instantly? The AI default uses Kafka, which is durable but adds hundreds of milliseconds of disk latency. An engineer uses Redis pub sub or Erlang distributed passing to keep it in memory. That is episode 4. The architecture that makes real time actually real. Subscribe to ByteLearn for the complete one engineer system, WhatsApp edition, one system design constraint per week. Every Tuesday, hit the bell. See you Tuesday. Question: which encryption concept surprised you most? The double ratchet. Drop it below. I reply to the first 10